I want to start with maybe a simple question. So let's say we want to test if we have a given die and that it's fair. And let us suppose I have a 10-sided die, or to any fellow Dungeons and Dragons nerds out there, a D10, with sides labeled with digits from 0 to 9. And we would normally roll this an arbitrary number of times, and then I'm going to pretend that I can magically roll it an infinite number of times and record it. And this will generate some sequence of values, A1, A2, A3, and so forth. And then we want to use a statistical test to apply to this sequence to determine if the die is actually fair or not. Now, of course, this is not going to actually work, because even a perfectly fair die could at times produce a sequence that's just nothing but zeros. And also, if I have an unfair die, then it could sometimes produce a sequence that's statistically indistinguishable from that of a fair die. However, these edge cases have probability 0. So our thought is going to be that a sequence shows that a die is fair if it matches the statistical behavior we expect to see from a fair die with probability 1. And then, well, once we kind of decide that, then we have to ask ourselves, what statistical test do we want to actually apply? What makes the most sense? Now, the most immediate one we have is that, well, on a 10-sided die, all sides should come up equally likely. So 0 through 9 should all appear 1/10 of the time. Now, we have to modify that a little bit because our sequence of digits is infinite. I can't talk about truly what does it mean for something to come up 1/10 of the time. So I make this into a limiting frequency. So here I'm counting the number of I up to n, where a sub I matches a particular digit d, divide that by n and take my limit as n goes to infinity. And provided this matches 1/10, then we're going to say, oh, this looks like it's acting like a fair die should. Now, there are many ways of calculating a limiting frequency. I'm using kind of the most basic one. If you want to do something more complicated, because, well, you can never do anything simply, look up the idea of Fulner sets and start heading in that direction. And then another natural test we might have is that the rolls of a fair die should be independent from one another. Just because I roll a 3 right now does not mean I roll anything particular the next time. If I roll a nat 1 on a d20 one time, that does not mean I'm cursed to roll nat 1s for the rest of the session. No. So, we want to ask, well, let's consider a sequence of digits, d1 up to dk, that all are from 0 to 9, and I want to say, how often do I see that particular sequence of digits appear and look at a limiting frequency there, and we say this should occur 1/10 to the k times if I'm looking at k particular digits. If we do this, then basically we're asking, do all the expectations that could possibly be asked of this match the desired behavior? Now let me change my perspective just a little bit, because I've been talking in the realm of dice rolling. So now let me talk a little bit about some dynamics. So let's consider a transformation T that goes from 0, 1 to 0, 1 that's given in the following way. T of x is just 10 times x mod 1. This has the effect of you take your base 10 expansion, you shift all the digits forward one place because you're multiplying by 10, and then because it's mod 1, you erase the first digit. So A1, A2, A3 becomes A2, A3, A4. But this transformation has been wildly studied throughout the years. It is, among many other properties, ergodic. And the pointwise ergodic theorem then tells us that if I have any interval A, and I look at, take your x, repeatedly apply t to it, and check to see if it's an A, the number of times this occurs as a limiting frequency should approach the length of your interval A for basically almost all points x. Specifically, if you have a generic point, that's exactly what this should do. Now let me pick a very specific interval A, namely an interval that looks like this, where d1, d2 up to dk is assumed to be a concatenation of the integers, not the product of the integers. So if I have 309, this would go from 309 over 1,000 to 310 over 1,000. And then we can very quickly see that, well, if I shift my decimal expansion forward, I times, and then check to see if it's an A, this will occur precisely when a sub I plus 1 up to a sub I plus k matches d1 up to dk. So in this case, asking for this ergodic result to match what we expect is exactly what we were talking about before with this limiting frequency of our digits. So as a result, we kind of say this is a nice special property, therefore it should have a nice special name that we haven't used 50 other times in mathematics. At one point I tried to look up how many different uses of normal there were in mathematics on Wikipedia, and I think I stopped after about 25. So, a number, x, which satisfies the condition for all intervals a, or equivalently, whose sequence of digits satisfies the latter condition for all finite strings d1 up to dk, is said to be normal. And because I kind of started this off with this very generic question of what sort of statistical questions could we ask, let's consider that in this context as well. If we simply want that all single digits appear with the correct limiting frequency, so 3 wants to occur with the right frequency, 4 wants to occur with the right frequency, but I don't say that 34 has to occur with the right frequency. That is known as simply normal. And if we want that all strings of digits appear with the correct limiting frequency, that was the thing we just talked about, that's normal. We can also then say, well, that's just expectation. What if we ask about variance? What if the variance matches what we would expect coming from things like the strong law of large numbers? Well, in such a case, then we would say the corresponding number is now strongly normal. And then if we want to apply every conceivable test that could be asked of a sequence, asterisk there because how many tests can you actually ask? This is a property of numbers that's known as algorithmically random. And as far as I'm aware, the sets of numbers with each of these properties is a full measure set. There's lots of them. And let me show you some examples. It's very easy to construct simply normal numbers because all I expect is that the numbers from 0 to 9 each appear 1/10 of the time. Simplest example I can possibly come up with is simply take 0 through 9 and repeat over and over again until you're sick of it. This is simply normal, but it is not actually normal. String 11 never appears in this because it's periodic. There are many constructions for normal numbers. We'll see many of them later on. The earliest explicit example we have is due to G.G. Champernowne in 1933. Fun fact, he was an undergrad when he did this. He was also a friend of other famous mathematician, Alan Turing, who also worked on the question of normal numbers. And he showed that very simply, you just take all of the integers from 1 to infinity and concatenate them one after the other. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0, 1, 1, 1, 2, 1, 3, and so on. And the end result is normal. So not only do all single digits appear with the correct frequency, but all pairs of digits, all triplets of digits, and so on and so forth, all appear with the correct frequency in this. Now, much more recently, people have looked at this from the strongly normal case. Does the variance match? And the answer is no. This is too nicely ordered. It never kind of goes out towards that maximum variance we would expect from the strong law of large numbers. In fact, I don't know of any nice examples of strongly normal numbers. I am aware of the paper which says they should be basically everywhere. And that's it. Welcome to the frustrating part of working with normal numbers. They're everywhere. Can you exhibit them? I'm also only aware of one algorithmically random number, and this is Chaitin's constant, the halting probability of the universal Turing machine. By the way, I encourage you, if you have a chance, to go look up the proof of this fact, because it's not terribly long and it feels like they cheated. Because basically the way the proof goes is, well, if it weren't algorithmically random, there would be some amount of pattern to the digits of Chaitin's constant, which means you could do some amount of prediction of the universal Turing machine, which is not possible. There we go, it's algorithmically random. And outside of rationals, which are not normal for reasons we just expressed, and Chaitin's constant, we actually know very little about the statistical properties of the digits of most commonly used numbers. I worked on the digits of square root of 2 in base 2, and I improved the results so minutely I felt like I had wasted 3 months of my life. We know very little about all of these. Of course, pi being so famous, it's one that we've done lots of statistical studies on. In fact, when ENIAC was built, one of the first things that we did with it was try to compute a whole bunch more digits of pi in the hopes that we would find some more evidence that it's normal or not. All evidence still points to it being normal. Do we have a proof? No. So let's talk a little bit more about Champernowne's constant. Why is this actually a normal number? Well, let's suppose we consider a given string, d1 up to dk, and a small value of epsilon that's positive. Now, by basic combinatorics, and again, I'll put basics in air quotes here, we expect the number of very long strings, much longer than s itself, length n, to contain s with frequency outside of this expected interval to be vanishingly small. In particular, this should go to 0 exponentially quickly as n goes to infinity. This has one of my favorite names of a lemma in all of mathematics. This is, I must say this like I'm a Viking, Horstings inequality. So if we concatenate all strings, so all finite integers, we will see the limiting frequency of s should be, basically within epsilon of the desired amount. And then we let epsilon go to 0. Now, of course, this isn't perfect because this is counting things like, well, here I can find a copy of 1 and 1, where one of these starts in 11 and the other starts in 12. But it turns out that's not a big deal because once your strings are very long, who cares if you see a couple that kind of overlap two different numbers? What is inside a given number is really what counts. And then, of course, the moment someone does this, lots of people have to follow on, and there's basically a cottage industry of people who work on normal number constructions. So just to list a couple of them, Besakovich showed that if you concatenate the squares, this works. Copeland and Erdős showed that if you concatenate the primes, this works. Schusch and Volkmann have a fairly general result, part of which is to say that if you concatenate the floor of the square root of n, this works. If you concatenate the largest prime factor of n, then De Koninck and Katai proved that that's normal, and then Paul Pollock and myself worked on this problem. We showed that if you go look at your classic Euler-Toscan function from undergraduate number theory, well, that turns out to give you a normal number as well. And there's lots of other different methods that have popped up. There's one method that uses harmonic analysis to say, well, actually the problem of that can be expressed in terms of exponential sums. And if we can show that all of these exponential sums are small, then we get that the number is normal. And this has been used by a variety of people. Davenport and Erdős, there's that Erdős guy again, showed that concatenating the values of integer value polynomials works. Nikai and Shiyakawa did the same thing, but basically said, well, you can look at polynomials evaluated at primes rather than polynomials at all values. I have an absolutely crazy result. This was, I think, my first result I published in grad school, which says if you concatenate little omega of n, which counts the number of distinct prime divisors of n, then you get a normal number, but only if you concatenate the second half of little omega of n. If you do the first half, Erdős-Katz's theorem says it looks too much like log n, which grows so slowly it ends up not being normal.
Is half important?
Yes, because it's that one half that if you start looking at the first half, that's where Erdős-Katz's theorem comes into effect. If you look at the second half, Erdős-Katz's theorem can't tell you darn thing about it. There's a bunch of papers, kind of starting with Stoneman and Korbov, that got generalized by Bailey and Crandall, looking at numbers like this. And this is basically related to the fact that the base 10 expansion of 1 over 3 to the I is very, very nice as you keep increasing I. In result, you can show that this is going to be normal.
If 3 changes to 2, what's happening?
Nothing good. The main issue there is that 1 over 2 to the I doesn't behave quite the same way because 2 and 10 share a prime factor in common.
So does 7 work?
1 over 7 to the I times 10 to the 7 to the I? Yes.
Okay.
So let's go back to our original question. We were talking about a 10-sided die, but what if we did the same thing with a 6-sided die or an 8-sided die, right? How do I tell if I'm going to get a statistically equivalent to random sequence of numbers coming out of this? Well, basically, everything we've just discussed is robust to changes of base, right? Just because I was talking about base 10, that's not really anything special. We can still define normality. We just change what strings we're looking for, because some new strings may appear if I add more digits or may get removed if I want to delete some digits. And we change the corresponding frequency we expect them to appear at as well. These constructions even basically work from base to base. So if I want to construct Champernowne's number base 2, 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, so on and so forth. Now note, this is Champernowne's number in base 2, which is not the same number as Champernowne's number in base 10. They are completely different numbers. But now, here's where I want to make things a little bit different. What if my die was actually unfair? What if I want to test for that unfairness? What if I want to do random testing to check that that's actually working that way? So let's suppose, just a simple example, let's say we have an unfair coin that comes up heads 1/3 of the time and tails 2/3 of the time. Could you still construct a sequence of H's and T's that is indistinguishable from a randomly generated sequence according to some statistical tests? To begin with, we could say it's easy to construct a simply normal sequence because I can do HTT, 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 HTT. Heads comes up 1/3 of the time, tails comes up 2/3 of the time. That matches what we expect. But what about fully normal? What about all sequences of digits in this case? Do they even exist? Well, I'm now going to once again transfer my thoughts over to the dynamic realm. So let's consider transformation t that goes from 0, 1 to 0, 1 that acts by 3x on the interval from 0 to 1/3 and by 3/2 x minus 1/3 on the interval from x being in 1/3 to 1. Now what you will notice is it takes both of these intervals and maps them to the whole interval from 0 to 1 in just a nice linear way. And this can easily, asterisk, be seen to be an ergodic function with invariant measure given by Lebesgue measure. We can extend this to a definition of an expansion for x, where a sub I equals 0 if my corresponding iterate belongs to 0, 1/3, and a sub I equals 1 if my iterate belongs to 1/3 of 1. So basically look at these two things as being 0 and 1. Then it turns out you can recover any point from its corresponding sequence, and also this has the same property we had before, where if I apply t to a sequence of digits, what does it do? Shoves them all one step forward. Now, this t that we described on the previous slide is an ergodic transformation. So once again, for almost all real numbers, x in 0 to 1, I can have this nice ergodic average holds for any interval a. So therefore, normal numbers, which correspond to normal sequences for our unfair coin, do in fact exist. So you could construct something where the sequence 0, 1, 1 should occur with a specific frequency, and you could measure out what that's going to be. It turns out it should be 1/3 to the first power, 2/3 to the second power, because that's 0 occurring with probability 1/3, 1 occurring with probability 2/3. That's what should happen. Now note, we had a transformation t from 0, 1 to 0, 1 to model basically a fair coin flip. Really, we did it with a fair die roll. We also just described this transformation t to model an unfair coin flip. Both of these are ergodic. Both of these have Lebesgue measure as their invariant measure. However, if we think of them as sequences in 0, 1 to the n, so just think about the sequence part, don't think about the nice continuous dynamical part, then we get two very different invariant measures here. So if you're the kind of person who cares about invariant measures, please know that there's a big difference between modeling things this way and modeling things that way. Okay, well, what if I go even beyond this? Well, we can discuss normality for basically any way you want to expand a number that you can think of. So in general, if I have a digit set, I like to call my digit set D, we say that a number x given by an expansion, that's a sequence, an infinite sequence of digits in D, is normal if for all finite strings of D1 up to dk, we see that sequence occurring in the first n digits, divide that by n, take a limit, so this is the limiting frequency of how often we see that. It should appear with this type of frequency, where in particular mu is some associated measure, and c sub d1 up to dk is the cylinder set. It's the set of points whose first digits are precisely d1 up to dk. And if there's a map T that acts as a forward shift on the digits, is ergodic and has mu for an invariant measure, then almost all x will be normal. This is again just a straightforward application of the pointwise ergodic theorem. So, some examples. I call these esoteric examples, even though I hope everyone in this room is familiar with continued fractions. If not, you will be now. Continued fraction expansion, 1 over a1 plus 1 over a2 plus 1 over a3, so on and so forth, where all of your a sub i's belong to n. This has a transformation t that's given by 1 over x mod 1. You can kind of see this because if I take 1 over this, I just remove that first 1 over. If I take this mod 1, I just delete that first integer that's out in front. The invariant measure, though, is a very fun thing here. I actually missed a... Oh yeah, this should be dx over log 2 times 1 plus x, so apologies for my typo there. Now this results in some strange expected frequencies because the expected frequency of 1 here is log 3/2 over log 2. That is not a nice number. Also, digits are no longer independent from one another, so if I look at the frequency of 2, 1 versus the frequency of the string 1, 2, these are not the same anymore. This starts to make everything a little bit tougher. Well, now I couldn't give a talk here without talking about beta expansions at least a little bit. So if I have the greedy beta expansion for beta equals 1 plus root 5 over 2, well, this looks like our standard base B expansions. You have a integer divided by a power of beta, except your beta is now an irrational number. Now, this has a nice transformation. Tx is beta x mod 1. The density of the invariant measure is given by this. It's just kind of a two-tiered thing. Here, however, certain strings are not allowed. We never see 1, 1 appear. You can never have a 1 followed by another 1. Nevertheless, almost all numbers here are normal as well.
Why this one is called greedy?
Because you can do various other types of beta expansion. It's not unique for them. Most famously, there's the greedy one and the lazy one, which are greedy one wants your digits to be as large as possible, as fast as possible, and the lazy wants them to be as small as possible early on. I don't know very much about anything besides the greedy one, because that's one I tend to focus on. Now, I had given you a number of different normal number constructions for base B numbers, but if I move to general systems, this basically all disappears. Much of this is because most of our methods are unique to base B, even though the B wasn't necessarily that important. The exponential sum method has no real parallel to other constructions. The method involving 1 over 3 to the I also has no parallel to other methods, so there's not much we can do there. All that we're left with is that combinatorial method, the idea that was started by Champernowne. So if we take another look at this one, for the third time now, the reason why this was normal is because basically if we look at almost all of the integers, they are close to normal in some sense. On a small scale, they appear to be normal. Well, this means immediately that almost all integers are not close to normal for any other notion of normal, because if I change my definition even slightly, everything that was normal should stop being so. Well, several constructions have sought to get around this by kind of repeating the good stuff. If I know that I have a finite string that's already close to normal in some sense, repeat that a lot because that's going to act like normal on a large scale then. And if you have something that's not close to normal, don't repeat it quite so much. So let's say we take a set that has all of our strings of length n, every possible string you can construct in your system. And let's form a new string formed by concatenating a whole bunch of these. So I'm going to choose some extremely large value here, multiply it by the frequency I expect to see of that particular string, round, because we got a round, and then take that many copies of that corresponding string. So I have a whole bunch of copies of S1, followed by a whole bunch of copies of S2, followed by a whole bunch of copies of S3, and so on and so forth. And we chose these particular coefficients in front of them, so the relative frequency of all of these strings should be about what we expect. And it turns out, because these systems tend to be nice, that this means if I look at any shorter strings, those should also appear to roughly the correct frequency here. Now you might hope that if I take these strings that we constructed on the previous slide and I just slap them one after the other, I should get something normal. Alas, no. Because the problem is that maybe I chose that kind of big integer I was multiplying everything by to be a little bit too big. So I just start with a huge number of repetitions of the same thing over and over again. Boring. Or worse, maybe I just indexed everything very badly and I stuck all the ones which are really terrible right at the front. Well, that's going to influence things very badly. So what we should do instead is now start to repeat those massively long strings a whole bunch of times. So take that big string from the last slide, repeat it a whole bunch, look at the one that involves 2 digits, repeat that a whole bunch, the one that involves 3 digits, repeat that a whole bunch, and so on and so forth. And you choose your MIs so that the length of any one of these is much longer than the first appearance of the next one. That will basically guarantee that when I start looking at this one, I still kind of hold on to the behavior of what I saw before until this one has time to go through its entire length. And if you choose your NIs and your MIs well, then this method basically generally always produces a normal number, even in some of these strange systems that we were seeing before. The first example I know of this is a guy named Bernoulli who did this in the 1970s. The most refined version of this I'm aware is by Madrich and Mance, who did this in 2016. However, if you look at the Madrich-Mance paper and you go through the details in it, which I have because I like Bill Mance, he's a cool guy, and I like his papers, I realized that when he had a single string of length k, he was repeating this on the order of k to the k squared times. That's how big his n and his m needed to be to make everything work. And in contrast, if you look at the Champernowne construction, every single string was only repeated a single time. Well, I was unhappy about this. And I kind of resolved as well, I should be able to do something like Champernowne that is a simple construction and still works. It's like, good job, Bill. I like your paper. I want to do better. And it turns out there have been some examples of such a thing. So Adler, Keen, and Smorodinsky proved a Champernowne-like construction for continued fractions. Basically, they arranged a sequence of fractions, 1, 1/2, 1/3, 2/3, 1/4, 3/4, 1/5, 2/5, 3/5, 4/5, expressed them in their continued fraction expansion, and then just concatenated all of those. Turns out, that's normal. And kind of seeing that led me to propose a conjecture. What if I arrange all of the strings, all the finite ones, in a descending order according to the size of their cylinder set? So I will see S sub I appear before S sub j if the corresponding measure of S sub I is larger than the corresponding measure for S sub j. Then I conjecture that if you concatenate all of these strings in order, S sub 1, S sub 2, S sub 3, and so forth, one time each should be good enough to give you a normal number. So in our biased coin flip example we had earlier, 0 has a weight 1/3, 1 has weight 2/3, and if you look at all of the possible sequences you will get out of this, they get arranged in basically this order. So that has weight 2/3, that has weight 2/3 squared, which is 4/9, which is slightly larger than 1/3, which is slightly larger than, and so on and so on. You can go through all of this. So my conjecture is that should work. And then many, many years ago, I managed to prove this in some cases. Basically, I proved this if I have a system with finitely many digits and a simple product measure. And that is to say, the digits go from 1 to n, and there's a frequency, lambda sub I, attached to each digit I, such that what's this frequency for d1 up to dk? Well, it's just lambda of d1 times lambda of d2 times lambda of dk. And this corresponds to a dynamical system known as a Roth series. Now, unfortunately, the proof is awful. So basically, look at an n-dimensional Pascal triangle, cut it with a hyperplane, and then count everything above the hyperplane. Sum it all up. This paper is basically 3 pages of setup followed by about 20 to 30 pages of very deep analysis of trying to figure out what that sum should be. And that's how I did this one. I will not be giving you that talk today. I think when I was here back in about 2015-ish, I think I gave that talk. Everyone was asleep by the end. Sorry, everyone who was there.
What do you mean by n-dimensional Pascal's triangle?
So you look at not the you look at a multinomial type of thing rather than a binomial type of thing. And then you can create a nice ordered n-dimensional pyramid, basically. Okay. And then slice it with hyperplane and count everything above it. So now I want to tell you that I've done better. And I've done better in two ways. One, I've made the result better, and two, I've made the proof much better. So I'm going to say now that the conjecture is true if we are in a system with a simple product measure and a finite entropy. So in particular, I no longer restrict myself to having a finite number of digits. I just need a countable number of digits. Now I also, however, need that this right here, lambda sub I times log lambda sub I is finite. How many people here know about entropy? You know what entropy is? Okay, you're doing better than me. The classic result, the classic statement about entropy is Claude Shannon, who was an information theorist, was looking at an invariant that looked like this and didn't know what to call it, and was talking with someone else, and that person suggested, oh, we should call it entropy, because no one actually knows what entropy is, and so you'll be invited to give lots of talks to explain it. Shannon took his advice. So, yes, I have replaced the finite digit criterion with the finite entropy criterion, so now I can allow myself to have infinite digit sets. And also I've replaced my incredibly difficult proof with a much simpler and straightforward one, which I will attempt to give you the basic gist of now. So to begin with, let's assume that my digit set is infinite, because I already have a finite case covered by my other terrible paper. Let's let it be organized so that lambda 1 is greater than or equal to lambda 2, greater than or equal to lambda 3, and so forth. And because I don't want to write the subscript all the time, I will call lambda be lambda 1. So it's the frequency of the first digit. Now for an arbitrary system, it is difficult to calculate exactly how many strings S I should expect to see that have a particular frequency. However, I can look at this function. So W of X is counting the number of strings where the frequency I expect to see that digit at is in a particular interval. So it's between lambda to the x minus 1 and lambda to the x. And it turns out this function is actually fairly well behaved. So to begin with, it satisfies a nice recurrence relation. So if I look at W of X, which is counting how many strings, again, have their frequency about at size x, well, that's a sum of a bunch of other W functions, x minus log lambda I over log lambda. And this just simply comes from the fact that if you start with a string S, you can always just kind of take off the last digit. So write your S as S prime concatenated with a single digit D, then that S prime will be counted by something smaller, because its length is going to be slightly smaller than the length of X, and it turns out if you calculate exactly what it should be smaller by, it's that. Add up all the possible combinations of different last digits, and you get our formula right here. Then, once you have that, you can show that your W of X function actually satisfies a nice asymptotic bound. Now, if you've not seen this notation before, what this means is that W of X is kind of bounded above and below by a constant times lambda to the negative X. So it's pretty darn close to this thing. So to begin with, I'm going to define a related function, f of x, that I'm going to let be lambda to the x times W of x. Now, if my proposition is true, and vice versa, it should be that f of x is on the order of 1, because I basically move that lambda to the negative x over to the other side. Now, we can just look at the definition of things and find that it turns out f of x is on the order of 1 when I'm between 0 and 1. So I get it for a very small range. I want to show it for all of them. Now it turns out the recurrence I have for W gives us also a recurrence for f as well. So let me start here. F of x is lambda to the x times W of x. That's just the definition of f. W of x has a recurrence relation, so let me just write that out. Then let me reverse and use my definition of how to go from W to f now to include that. And you notice something a little bit magical occurs here. Lambda to the x, lambda to the negative x, those cancel. Even better, I have lambda to the log lambda I over log lambda. Play around with the logs a little bit. That's just lambda sub I. So it turns out that our f of x function satisfies a very similar recurrence. It just has a factor of lambda I in front of all of the terms. Now for an upper bound. F of x equals this thing. And now we're going to employ one of the kind of classic techniques, I want an upper bound on this, yank out the largest thing that could be there. So I'm going to say, well, I'm going to pull out the largest that my f can ever be and stick it right here. And then this is going to be just the sum that's remaining. Well, it turns out, basically by the way you can set this up, that your sum of your lambda i's always equals 1. You can always assume you're working on the interval from 0 to 1. So I just get that f of x is bounded by the maximum of a smaller value of x. And from here, well, we already showed that f was bounded on 0, 1. So that you can therefore show it's bounded on 0, 2. Therefore show it's bounded on 0, 3. Leave as a basic exercise introduction to the reader that it works for everything. The problem, however, is that lower bound. Because if I try and do the lower bound here, I can't just stick in anything over here, because it turns out a bunch of these f values are going to be 0, and I know that. So instead, I have to sneak up on this problem. So I know that I should get non-zero things if I let lambda I be larger than or equal to lambda to the x. So this is a partial sum of what I have here, and I'm going to have a bunch of f terms here that are non-zero, but one of them smaller than the rest. Now, I don't know which one it is, but I can say, this thing here, this sum, let me call that 1 minus epsilon sub x, because I know it's going to be close to 1 because I've summed up most of my lambdas. So I get something like this. Well, the moment I have f of x being bounded by itself, I should iterate. So let me call whatever value kind of minimizes this, my x sub 2, let x be x sub 1, just to kind of make things consistent. So I get f of x is greater than or equal to 1 minus epsilon of x1, f of x2. Well, now I can apply a similar bound f of x2, and that will give me this right here. I can define an x sub 3, an x sub 4, an x sub 5, and keep repeating this. And at some point, this has to terminate because for some value of xn, we'll end up in 0 to 1. And we've already said we know that f of xn should be greater than or greater than 1 at that stage. So combine the last slide's ideas together, we get that f of x is bounded below by some product of 1 minus epsilons. Well, we can play around with these epsilon values. We know that 1 minus epsilon sub x is increasing in x, and moreover, every time I go from xi to xi plus 1, I have to decrease by at least 1 every time. So let me do the absolute worst case scenario of getting every possible integer up to x. I hit all of these. This is the worst it could possibly be. Well, now we make use of a very important formula, which is that 1 minus z is bounded from below by e to the negative 2z, at least for most of them. So now I can transform my big product here, because all the products are of that form, into e to a sum. So if I can show that that sum is bounded away from infinity, then we've shown that f sub x is going to be bounded away from 0. Well, let's peel off definitions. What is epsilon sub m? Well, it turns out it's the sum of the lambda i's that are at most lambda to the m. Make use of the fundamental theorem of analytic number theory. Reverse the order of the sums. And it will become this. We get the sum over lambda i's, the sum over I, lambda I, and then a minimum of either x or lambda log lambda I over log lambda. And if I see a minimum like this, well, I just assume it's the worst part. So this is at worst, this thing here, and oh my, that looks so familiar. Sum of lambda I log lambda I, that is going to be my entropy, which I assumed was finite to begin with. By the way, when I started working on this problem, I had no idea I needed finite entropy. I kept getting to this point and going, I don't think I can do any better. Sometimes an important skill in mathematics is knowing when to cut your losses. I couldn't prove anything better, so I'm just going to assume finite entropy and go from there. Okay, so now we know that this w function is bounded by this kind of nice bound on lambda to the negative x. But that seems a little bit like a distraction because that only counts a number of strings. It doesn't tell me how often I see a particular substring. So for that, let me introduce another bit of new notation. Let me call this L sub s of x. And that's going to count the number of times s appears within other strings, and those other strings need to be in this particular interval, according to their measurement. If I have no subscript, I just want that to be the total length of things. And then it turns out we can show that for any string s. How often do we see that? Well, it should be roughly our expected frequency times x lambda to the negative x. And then we can similarly bound L of x itself that way. And it turns out that L of x is a lot like measuring L sub s of x, where I treat s as the empty string, except there's an off by one error, because essentially I could have one more empty string than I could the length of the actual number. Okay, more combinatorics time. If I want to bound that thing, the trick is to say that if I've got a string capital S that contains a copy of little s, then I can write it as u little s v. Some little string, some other little string, s in the middle. Maybe I could even do this multiple times. But because my measure here is multiplicative, I know the measure for capital S is the measure for u, times the measure for little s, times the measure for v. So if my measure for capital S belongs to this interval, I know that the product of the measure for u and the measure for v must belong in this interval right here, where m sub s is chosen to be this thing right here. And conversely, if I have a pair u and v that satisfy this thing, then it turns out usv must be counted by my L sub s of x. So all I have to do now is count how many u's and how many v's together have that happen. Well, it turns out it's not as perfect as you want it to be, because all of my counting things say basically count something of length 1 in the exponent. If I multiply two such intervals together, I am now counting an interval of length 2. So that's a little bit of a problem. But it's not a terrible problem. Because if you just kind of work at it a little bit, you can get an upper bound like this. Basically, I say, assume that u belongs to w of n, then you can show that v has to belong to one of these two. Sum up over all possible values of n. Conversely, we can get a lower bound by saying, well, let's say u is counted here and v is counted here. Well, you might have not quite hit ls of x, you might have hit ls of x minus 1. So we have to lower bound it that way. But now, make use of the fact that w of x is bounded this way, and you can very quickly get that L sub s of x is bounded this way. It's just basically a bunch of algebra at this point. Okay, now I've told you how to deal with w, I've told you how to deal with L sub s, we can finally actually check for normality. So, let's look at some little s, which is d1, d2 up to dk. This is some fixed string, and suppose that n is some very large integer. The nth digit in that big concatenation of strings appears in some string. Call whatever thing that is t, and let's say that the measure of t is x. So then if I count, how often do I see my string s? Well, basically, it should be the number of times I see s in strings that have length up to x, divided by the total length of all of those strings. Again, I'm fudging this a little bit because, well, I'm not counting things that start in one string and end in another, like we saw way back when. But that's not relevant for the moment. This becomes, look at an upper bound and a lower bound, use the facts we had from a previous slide. Well, that just turns out to be mu of c of s. Seems like everything's golden, right? Whenever a teacher says that, you should immediately shake your head. Because the problem is, all I've shown is an upper bound. I've shown that the frequency here is bounded from above by the thing I actually want. I haven't shown what the actual limit is. However, Piotowski-Shapiro comes to our rescue. Because there's a great result, and I'm here giving you the base 10 case that says, well, let's say you try to show something is normal, but all you can manage to do is show that you are within a constant multiple above where you're supposed to be. The lim sup of your frequency is no more than a constant more than it should be. Well, it turns out you actually were normal. Basically, what Piatowski-Shapiro showed is that you can't be too close to normal without just being normal. If you tried to get close to it, you just kind of snap onto it completely. Well, that's great. And in particular because the Piatowski-Shapiro normality criterion has been extended to other systems. Moshevitin and Shkredov did some work on this. There's a small error in their paper that was fixed by Dylan Airy and Bill Nance. This was actually noticed by Dylan Airy because, of course, if you want someone to find a fault in a paper, hand it to an undergrad and ask them to explain it. They will find every mistake in that paper. So we showed that we got within a uniform constant of the thing we wanted. Piatowski-Shapiro then says, you actually have to be normal. There's no other option. You were too close. So our construction that we gave before does actually provide a normal number. Well, I've given you the proof. Now let me give you all an open question. And I can come back and you can all teach me something. I have a finite entropy condition. And as I told you before, at some point you knew when to cut your losses and you stopped trying to prove something harder. But is it actually necessary? Are there counterexamples to my construction if we ignore this finite entropy condition? It was very critical to finding the lower bound for W of x, and hence for L sub s of x. And without it, the denominator in that lim sup calculation could be far too small to actually properly bound everything. And basically, if we have an example of a system where we don't have finite entropy, that's usually where, you have a couple of digits and you're just acting on those digits for like millions and millions of times, and then, suddenly you have an explosion of new digits that are completely altering the behavior. And this happens again and again and again. So it's possible every time you do this and you add in these new digits, that you're just completely destroying whatever frequencies you had before and everything is changing. But I've not been able to prove that yet. That's the end of my talk. Thank you very much for coming.
Thank you very much. Very interesting talk. Any questions for Joe?
Can you go back to slide 47? So, is this relying on the fact that we're having finite many digits?
No, Piatowski-Shapiro does not rely on that. However, the error that Dylan Airy found was that Moshevitin and Shkredov basically assumed that you had finitely many digits, and so you needed to tweak it just a little bit to what happens if you have many digits.
Okay.
Because basically there's a silly example that satisfies the condition, but clearly isn't normal. You could just have the sequence of digits 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Keep doing that. It clearly satisfies that because in fact your lim sup is 0, but it's not normal.
Right.
So Airy had to fix this by basically saying, no, you actually have to have, things do have to appear with an actual frequency. And the moment that happens, then everything works.
Okay.
Steve?
So if you don't have a product measure, but in the more general case there, is there any do you know that conjecture for continued fractions where you when you're writing on decreasing cylinder measures, is that?
I don't know it in that case. You get very close to, because the continued fractions are so nice, they almost act like a product measure, but it's not perfectly.
Yeah, right, like an exponential decay to the independence rate, so it's
Yeah.
that's not enough to.
Not that I found yet. In part because I haven't tried to extend it past here. It's possible that, I have lots of places where I could potentially fudge things and say, well, you don't need it to be exactly this, you can be off by a little bit, but I haven't actually tried to make that work yet.
Is it easy enough to say what the definition of algorithmically random is?
No.
So,
The basic definition that I have heard is that you want to satisfy every possible test that you can write out.
And what was your example of the?
Chaitin's constant, the halting probability of the universal Turing machine.
Doesn't it depend on how you code the Turing machine? I mean,
Well, it's the universal Turing machine, so no.
but you still have to code the Turing, whether it's universal or not, you have to code it, don't you? I mean, how do you, you say.
You're asking me questions about Turing machines, and I'm not an expert on Turing machines, so I will have to.
I mean, if you chose a totally different way to
You
represent
could code it. in
Yeah, you code it in some
a
totally
way.
different way, you probably totally alter the probability, right?
I don't think so.
Well, I'm not sure how to define that. Okay, yeah, but anyway.
Again, not my area of expertise.
I have a question. So does your theorem apply to the Gauss map, the continued fraction?
No, because that one doesn't have a product measure.
Oh,
Yeah. You can look at variance, you can look at the Roth series, which would have a product measure that are related to the continued fraction expansion, but I don't have an actual result like this for continued fractions yet.
And then is there knowns to be something that's strongly normal but not algorithmically?
I am not aware of any. Surely we would conjecture such a thing must exist,
Yeah.
but we don't even have nice examples of strongly normal numbers, let alone examples that are strongly normal but are not.
So there's no existence proof either.
Can you give the precise definition of strongly normal? In what sense?
Off
The
the
variance.
Off the top of my head, no. Basically, just ask that you want the strong law of large numbers to hold. So you want that the variance occasionally gets
Well,
as high or
The
as small.
strong law of large numbers only talks about averages, so you mean like something like law of iterated logarithm, or?
Maybe that's what I mean, yes.
But it's not
I don't remember the
conditions of
exact
like the
form.
third and fourth and fifth moments or whatever as well? Or is that part of that definition?
I think it only cares about the second one. And then, you expect the second moment to occasionally get so high and then occasionally so small, and you want to show that your number actually does match those. And the problem with something like Champernowne's constant is, in fact, the second moment is very close to zero basically all the time.
Any other questions? Josie?
I know that you build some known numbers. Do you know some measure information about kind of numbers, like how about the Hausdorff dimension of all the kind of the sum of all these kind of numbers? Do we know some about this?
Well, I mean, it's a full
measure
measure
one.
set, so, yeah, it should
Don't
be.
measure one.
Oh, so all these numbers form a measure one?
Yeah,
Yeah.
you don't measure one.
And dimension one?
Yes.
It's full dimension, and measure one, is there a measure?
Now, if you start asking for, is it this but not that, we've actually worked a bit on that problem before. We have a paper about things that are continued fraction normal but are not base B normal. And there you can show this is a fairly rich set that's not, it's measured zero, it has to be, but it does still have a lot of interesting complexities to it. It's a fairly complicated set.
Has anyone ever studied if Louisville numbers satisfy any of these?
Well, depending on the one you're talking about, sometimes the answer is obviously no.
Yeah, right.
Because like you have the one that's like 1 over,
Yeah, it's like 10 to the n factorial.
Yeah.
But like, what about like in base 2?
yeah, they're, because we don't know how the bases interact with each other.
Okay.
So if you take the standard Liouville number base 10, what does that look like base 3? I don't know. I would hope that it's normal, but I have no way to prove it. Like in our with the Jeopardy theme, while we go searching for this. Actually don't, because this will be recorded. Here, so 1 over 3 to the I has good properties, and we would also expect 1 over 10 in fact, to the n factorial to also have good properties in base 3. But you need this thing here for kind of the same reason that we had to have that massive repetition of things in that one construction.
Yeah.
Because it's possible that, sure, 1 over 3 to the I has a nice expansion, but if you just slap a whole bunch of those things right onto one another, they could start to interfere with each other and suddenly you lose all the properties that you had. you need that 1/10 to the 3 pi to give one of those terms time to basically be random before you introduce anything else.
What if you concatenated like n factorial?
All of our concatenation proofs basically stop at polynomial growth. We have rare exceptions of going any faster than polynomials. So like one of the open problems that's now over a century old, I think, is what about concatenating 2 to the n, right? So you get 1, 2, 4, 8, 16, 32, 64, 128, 256. What happens? We have no idea. Do the Fibonacci sequence. We have no idea.
That's a great undergraduate research project.
No, don't do that to them. But conversely, sometimes you can have very, very small sequences that are still difficult to understand. A colleague of mine, because she works with it a lot, asked me about the Stern sequence. And the Stern sequence is a very slowly growing sequence that oscillates a whole bunch. And you get lots of repetition of things, so she thought it would be perfect for this. And I spent a couple of weeks on this and determined it was an extremely hard problem to answer, and I have not been able to do so yet.
Okay, any more questions? Well, let's thank Joe one more time.